Hi, Francis. Great.
I know you're trying to get organized.
We'll talk to you later.
Okay, that'll be good.
So where's Marty and Carol?
Hello. Hi, everyone. If I could get everyone to please make it to your seats. We will be starting shortly. If everyone could please make it to their seats. Dr. Pettigrew, still want me to announce?
Let's get Carolyn May.
I'm still going to sign the Ladies and gentlemen, the inaugural Dean of the School of Engineering Medicine, Dr. Roderick Pettigrew.
Thank you, Amy. Thank you, attendees. Thank you to the students and your marvelous posters, presentations that you just gave. It was such an enthusiastic group that I was concerned that we really hadn't planned quite enough time for it. But there's never enough time when you're having fun and when you're learning. I want to thank not only the students and those of you who have come out to support the students and this next generation of innovators. I also want to thank those who have supported us philanthropically. Judy Allen is in the audience, and we want to thank her. Stephen Ash, he hasn't arrived yet, he's on his way. And we have two individuals whose names are actually synonymous with EnMed, Craig Brown and Sue Smith. So if you think the poster session was exciting, and indeed it was, and it was inspiring and illuminating, indeed it was, we have another treat in store for you right now. Today we mark an historic occasion. A new experimental educational paradigm envisioned several years ago had as its North Star the transformation of healthcare through the convergence of engineering and medicine. The central idea was and is to purposefully train physicians with the understanding and skills to be medical problem solvers, healthcare innovators. This was the EnMed program. It began in earnest in 2019 with 25 bright and adventurous and incredibly good-looking trailblazers. See what I mean, right? Tomorrow, we graduate the first class, the world's first class of physicianeers. To help us recognize this milestone and inspire the graduating class and the classes to follow, and the school to even greater levels of achievement, we have a remarkable gathering of some of the world's most impactful scientists, innovators of our times, and global thought leaders, 5 Nobel Laureates, and a National Medal of Technology laureate, co-inventor of the Internet, who will participate by Zoom in what promises to be a stimulating discussion of themes and sharing of ideas. This will be led and moderated by the President Emerita of one of the world's foremost institutions of learning and technological innovation. And that's not just because I went there, it's because it's true. MIT. This is a rare gathering of accomplished wisdom, and we are immensely grateful that they have chosen to participate, to help us celebrate and learn. And I think this is important for us, to become a part of our history. Now, looking at the screen, this reminds me that one of our discussants is not on the screen yet, Vint Cerf. So if the AV team could help remedy that. There he is. Welcome, Vint. At this point, it is my distinct and quite rare honor to welcome to our campus, and this is in alphabetical order, Dr. Carolyn Bertozzi, Nobel in Chemistry, 2022. Dr. Marty Chalfie, Nobel in Chemistry, 2008. Dr. Susan Hockfield, President Emerita, MIT. Dr. Philip Sharp, Nobel in Physiology of Medicine, 1993. Dr. Vince Cerf, who you see on Zoom, National Medal of Technology and a co-inventor of the Internet. And by way of a video message that has been recorded, Dr. Carl Wieman, Nobel in Physics, 2001. Carl desperately wanted to be here in person, but for medical reasons, he could not. We've given him a rain check, and we appreciate his succinct and telling comments by way of video. Later this afternoon at about 4:15 or so, Dr. Peter Agre, Nobel in Chemistry 2003, will join us by Zoom. Dr. Agre is no stranger to us. We welcome him back to the School of Engineering Medicine. He participated in our inaugural event in the fall of 2019, and it is fitting that he joins us today to celebrate EnMed's first graduates. We look forward to hearing from them in two major thematic areas: pathways to excellence and the value of convergence and what the future may hold through infusing the healthcare system with physicianeers and similar convergent trained innovators. I would like to transition, and Andrew, this will be the first video, from the poster session to this discussion with a brief video from students in the class of 2023 on their experience in and perspective on EnMed. Andrew, first video, please.
I'm Zach Richards, current EnMed student and class officer. It's an honor to host you on a tour of the outstanding opportunities that await you in the EnMed program. Along with a couple of my fellow classmates, I hope to provide you with information that will be as fun and informative as an in-person walk through our program. Like many aspiring physicians, my goal in medicine is to enrich my future patients' health and well-being, but my dream goes so much further than just providing established standards of care. I have discovered a personal passion for medical innovation, and I needed a program that cultivates that passion into real benefits for patients. EnMed is that program. The student experience goes so much further than the classroom. I'm not just learning about the biodesign process, but actually working through it with projects that I get to choose. Whether it's developing software to streamline N95 fitting during the COVID-19 pandemic, designing an open source ventilator for low resource areas, or rethinking the way we approach visual field testing, one thing is for sure, I am an innovator now.
You have to learn the science of medicine to be a good doctor, but affecting change in the medical field takes something more. I studied biomedical engineering at Johns Hopkins and prepared to build the technology that could treat conditions in ways once thought impossible. I then earned my MBA to discover how to commercialize, market, and manage those innovations in order to reach more patients. Ultimately, I realized that the impact of any startup I launched or any hospital operation I improved depended on the doctors themselves. To drive a real change in medicine, I needed my white coat. Texas A&M's EnMed is founded on interdisciplinary principles that can drive sustainable innovation in healthcare. The chance to join the largest medical center in the world, practice at the #1 hospital for patient care in Texas, and share ideas with Texas A&M's unmatched alumni network was an opportunity I just couldn't pass up. My future goals surpass practicing medicine as it's taught. I want to change the way medicine is practiced to fit the changing needs of our patient population. Medicine is dynamic, and our physicians should be too.
Doctors are smart people. If you ask pretty much any doctor if they have any good ideas for new devices or procedures, they're likely to flip over a napkin and draw out a schematic for something that could potentially help patients around the world. What makes EnMed special is that it gives the doctors of the future the ability to make those napkin drawings become reality. EnMed is unique in its deliberate curriculum design to put the tools necessary to innovation into students' hands, including validating clinical needs by collaborating with experts at Houston Methodist Hospital, creating prototypes in our makerspace, and learning how to navigate regulatory and market pathways in order to make your bright idea a reality. As someone who is extremely passionate about increasing access to healthcare for underserved populations, I know that the creation of innovative medical technology will only grow in its role as a way to steward the wellness of our communities. With that in mind, I chose EnMed because I believe that the unique curriculum will prepare me to not only be an effective doctor, but also a purposeful innovator.
Those are our students. I'll now hand over the microphone to our esteemed moderator, Dr. Susan Hockfield, who herself represents Convergence as a neurobiologist who became the president of a premier engineering institution. Dr. Hockfield.
Well, I have to say it is truly a delight and a real honor to moderate this panel on this. Wow, okay. I mean, let me just start again and just tell you what a delight and honor it is to moderate this panel. I am incredibly excited to be here on this important occasion. And I'm joined by four amazing panelists. Find their full bios are in the program. But all of them, all of these on the stage and with us virtually, are in what I call my most awesome humans club. And each of them brings perspectives that illuminate possible paths to our graduates and all of our shared future. Now, I'm personally enthusiastic, I would say wildly enthusiastic about this joint program between Texas A&M University School of Engineering Medicine with the Houston Methodist Hospital. And I am as wildly optimistic for what this first class of physician engineers will pioneer for the world. This domain in which the program operates and this first class of graduate enters represent, to my mind, one of the most promising avenues to the future. I have spoken and written about the emerging convergence of engineering, biology, and medicine. There has been a deluge of discoveries in biology that have opened a new vast toolkit to solve technology's greatest challenges. This toolkit is truly amazing in terms of its possibilities for next generation medicines and medical devices. As a Convergent colleague of mine told me, this was a man working on water filters using biological tools. He said, you know, I could bust my brain trying to design a new water filter. He said, you know, or I could use nature's genius to do it for me. So that theme has just haunted me since I first joined MIT back in 2004, where I found people who were already operating at this fantastic interface. Now, up until now, the convergence of these different disciplines has relied on serendipity. But instead of that serendipity, today we now have EnMed, which deliberately and intentionally educates and exposes trainees to both worlds. Today's first class of physicianeers will pioneer new paths and discover new territories that will change the face of biomedicine and medical practice. And we are so incredibly grateful for your buying into this program and your pioneering a new future for all of us. So we have a format which Roderick just laid out. We will have a discussion with our panelists, and then when we're finished with that, Peter Agre will join us to close the program. So I've got a couple of questions for our panelists, and we're going to call on them in turn. The first topic is that, to all of you, we hold your Nobel Prizes, national medals, innumerable other prizes in recognition of your accomplishments with enormous respect and awe. And we're going to start this conversation in terms of giving our new participants in this effort a view of what was the path to the accomplishments that you all have had. What is, if you could describe the path to your prizes, and hope you might include some of the surprises, some of the forward progress, some of the backward progress you encountered along the way. Oop, I'm going to change my mic break, but let me just, and we'll get that started. So Carolyn's going to get us started, and then Phil, and then Marty will join in. Carolyn, please.
Okay, so I'm Carolyn Bertozzi. First of all, congratulations to all of you sitting here in the first few rows. I love that you wore your white coats today so that we know who you are. I'm incredibly impressed with the posters that I saw. Just, it's incredible, especially when I think back to how unsophisticated I was as a graduate student myself, in the sense that, I mean, talk about a path that was meandering and very unintentional. I don't think I had much of a view about my future, my career, when I was at your stage. I was very much living in the moment, just trying to learn and solve some problems of modest significance, really only to me. And so I think maybe the short answer to the question is, I don't think there really is a path to a Nobel Prize. I think there's a path to things that we all want to achieve individually, and then once in a while, there's a side ramp where we end up with a Nobel Prize. But it's really not by intention, nor really could it be, I think. And for me, it started with falling in love with organic chemistry as a presumptive pre-med when I was an undergrad. I wanted to go to med school really just for lack of a better idea. I don't think I had much of a sense of what it meant to be a doctor. Everyone else was a pre-med, why not me? I think that was the long and the short of it. But then one has to take organic chemistry as a pre-med, which you all did when you were college students. And 99% of the students that take that class report that they don't like it very much. But then there's that 1%, and that was me, and I really loved it, and it just absolutely matched my brain waves in some way. So I committed myself after my sophomore year of college to learn as much organic chemistry as I could, with the hope that someday I could even be an organic chemist. And then it was a bit of a meandering path for me to get there, in part because this was the late 1980s. And at that time, the field of organic chemistry wasn't particularly open to people who were not of the majority phenotype, which at that time was white men. And so it took several years for me to find my way into a lab where I could learn organic chemistry, and it happened when I was in college. When I was in graduate school. So that's when I finally got my big break, and I got to be an organic chemist in a young lab of a new professor who only lasted 3 years in his job, and then he quit because of a health problem. So he was diagnosed with colon cancer when he was maybe 33 years old, which is very young and very unusual. And this puts us into the early 90s. And so I spent a lot of time in hospitals with him. We'd had group meetings in the hospital with him while he was in there having surgeries and treatments. And I was also in hospitals for other reasons, because this was the late 80s, early 90s, was a period of time when the AIDS epidemic was raging out of control. And you all have experienced what a pandemic feels like on a global scale. At this time, HIV was more of a local epidemic, and it was certainly quite prevalent in San Francisco, which is where I was in graduate school. So I had a lot of friends, who had basically an HIV/AIDS diagnosis, which was lethal at the time. So I was in hospitals a lot then as well. And that's where my interest in biomedical science really flared again. So, as an undergrad, I was a pre-med for lack of a better idea. But in grad school, having spent so much time with an advisor and with a circle of friends that were quite ill, I really felt that medicine, there was something very primitive about it and very frustrating, because nothing could be done to help these people. And then, of course, friends with AIDS died, and then my advisor ultimately lost his fight with cancer as well. So at that point, I committed myself to use chemistry as a tool to help improve human health and make new medicines and new diagnostic technologies. And that has been my focus ever since that time. And it turns out that one of the chemistry tools that we invented in my lab back in the late 1990s, in fact, caught fire and became useful in many ways across the interface of chemistry and biology. And that is what the Nobel Committee recognized me for with the prize. But it's just one part of a much bigger story, which is very much continuing towards a goal of making new kinds of medicines to treat cancer and infectious disease and improve human health. And I'm still on that path.
Thanks, Carol. Phil.
My path is not that different than Carolyn's. I got my PhD at the University of Illinois in chemistry. I loved organic chemistry, so I was one of those, and I love thermodynamics too. And putting the two together, I became a physical chemist at the University of Illinois, got my PhD, started reading about molecular biology. And boy, there were questions not answered. There were things we really did not know about. So I made a transition as a postdoc to Caltech with Norman Davison, who was also a physical chemist who had become interested in biological science. And there began to use the electron microscopy to study the relationship between DNA sex factors in plasmids, drug-resistant plasmids in bacteria. But at Caltech, I realized that the time had come when we could begin to understand human physiology at the level of genes and chemistry. And that was such a fascinating, fascinating possibility. We could understand how the brain works, how we think, how memory. We could understand the physiology and evolutionary relationships. I thought it was the moment to be transformational in biological science, particularly this issue of understanding human normal physiology and disease physiology at a chemical level and a gene level. So that brought me to Cold Spring Harbor with Jim Watson, a number of outstanding, talented colleagues, where I began to use a DNA virus, DNA tumor virus, that can cause cancer in animals, and it had genes that cause cancer, and to try to understand, using that DNA tumor virus, some of the physiology that the virus had to have in human cells to make these transformations. And that led me to the question, which seemed fundamental to all of this. How is a gene structured in these cells? And why was that a question? What was a question? Because there was so much DNA. The DNA in each of your cells is this long. Massive amounts of DNA for what we thought would likely to be 20, 30,000 genes, maybe 100,000 at the upscale. And all that massive DNA. And there was a hint. We knew about message from the studies in bacteria, but there was this very long RNA in these human cells in the nucleus, and we had no tools to answer the question of what was the relationship between that long RNA and what we knew was smaller RNAs in the cytoplasm. And I had DNA tumor viruses. I could isolate RNA. I knew how to do microscopy. Seemed like an answer, the question I could answer. And so we set out to do that with a number of outstanding postdocs and colleagues. Restriction enzymes just happened, so you could map with restriction enzymes. And then I moved to Cold Spring Harbor in '74 because I wanted to be two things: in a university and close to Dave Baltimore. Because Dave had an approach to mammalian biology and virology that was very similar. And that led us in '77 to do the experiment of taking a purified message and comparing it to the genome from which it was transcribed in adenovirus. And when we did the experiment, we saw these loops. And we understood that this RNA had to be pieced together by this process called RNA splicing. And that was really breathtaking because it said what we had learned in bacteria in general was correct. DNA makes RNA, makes protein. But how that went about, how that was executed in these cells was vastly different. And new processes had to be understood, new reactions had to be understood. And it was just, it was breathtaking. I couldn't even come close to grasping all the implications of the work, but I knew it was a stunning new beginning. And so I've spent the rest of my career trying to understand this, right? So, and then that was in '77, and I got the opportunity at MIT, which I want to remind these engineers, is that
Physicianeers.
Physicianeers. MIT, it's mind and hands. When you understand something, you move it into society to make a difference. And in '78, I was involved in starting Biogen, which was co-founding with a number of other scientists that took molecular and cell biology into society, solving problems, making products, making things that were useful. So those two events occurred just about at the same time. A remarkable time, but really, did I have any intention that this was going to win the Nobel Prize? No. But I can tell you, when I saw those 3 loops, I thought about it. So that's my story.
Thank you, Phil. Vin, can I call on you now, please?
Yes, you can, as soon as I find the unmute button. Am I audible?
Vin, you're like me. After, what is it, more than 2 years of Zooming almost all the time, I'm always on mute. I don't know how that happens.
Part of the problem is that there are multiple conferencing systems, and they don't all have the same useful interface. And it's, so, gosh, it's a challenge to follow 2 Nobel Prize winners, so I'll do my best. First of all, I love the term physicianeers because it really does draw both engineering and medical profession together. I have to tell you that I go to, when I can, an annual meeting of the Nobelists in Lindau. Some of you perhaps have already been there. I attended not because I have a Nobel Prize, but because I was invited to go as a representative of another meeting that takes place in September of the Heidelberg Laureate Forum for Computer Science and Mathematics medals winners. So we started exchanging lecturers. But what was particularly amusing, and perhaps the Nobelists on the panel will appreciate this, I went to one time when it was the physicists gathering. And of course, there are 400 students who participate in this thing, and the physicists were describing their work. And they got to the Q&A, and one student is levitating out of his chair. Did you know that you were going to get the Nobel Prize when you were doing this work? And the physicist said, well, let me explain that getting the Nobel Prize is 95% luck and 5% knowing how to do the math. So my little contribution here to at least the medical and engineering side of the discussion is to introduce the term computational X for almost every value of X you can think of, whether it's biology or chemistry or astrophysics or linguistics or sociological or computational sociological studies, and it just goes on and on. Computing has become a very core part of the way we do our research and the way in which we discover and share information. And of course, one of the ways we do that is to get on the internet and make use of the World Wide Web. So my story is mostly an engineering story. It starts in 1969, and I promise I will not go through 50 years of history in 5 minutes or something. The work was sponsored by the Defense Advanced Research Projects Agency, which was frankly interested in getting computer scientists to share their results so that we could accelerate the pace at which computer science and artificial intelligence were pursued. And this is literally in the 1960s. So we began finding ways of connecting time-sharing machines together using a packet switch network, which at the time was a heretical technology. Everyone knew the way you built networks was circuit switching, which is the way the telephone system used to work. So it was considered heresy, and we said, well, we're going to do it anyway. So we built the network to allow a dozen universities to share their results in computer science research. And that was so successful that the Defense Department said, well, why don't we figure out how to use computers in command and control on the theory that if you had computers to help you, you might be able to overcome a larger force with a smaller one, thanks to a force multiplier related to tactics and logistics and other things that computers could help with. Well, that immediately led to a problem because the system we had built called ARPANET was based only on dedicated telephone circuits connecting the packet switches to each other. My colleague and instigator of the Internet program was Robert Kahn, who was at ARPA at the time. And by the time he showed up in my lab at Stanford around 1973, he'd already started working on mobile packet radio and packet satellite in addition to the original ARPANET. And the problem that he confronted me with was how do we connect these different kinds of packet switch nets with different error rates and different latencies and different packet sizes, different addressing structures, so they all look like the same thing. And that led to the design of something we now call TCP, or Transmission Control Protocol, which eventually morphed into something called TCP/IP, where we split off a particular protocol, the Internet protocol, which is for low latency real-time communication, but which does not necessarily guarantee that all data is delivered, but it does get delivered as quickly as possible. The motivation for that is packet voice, packet video, packet radar. You don't want to know where the missile was. You want to know where it is now as near as possible. And so that evolved into a government-sponsored multi-network system. The National Science Foundation, the Department of Energy, NASA, and DARPA all built backbone networks which we interconnected with each other. So up until 1988, starting from 1983 when we turned this on, and 1973 when we started doing the research, it was all government funded. The only people who could get on board were those with government contracts. So at that point, I started scratching my head thinking, well, how are we going to get the general public and the private sector up on systems like this? And we found a tactic to break the appropriate use policy, which said no commercial traffic on the government backbones. I proposed to interconnect the MCI mail commercial email system to the internet as a test. Of course, the real reason was to break the appropriate use policy. And I got permission to do that. That in 1989, we turned that on. All the other email carriers said, we want to be on board. And by late 1989, 3 commercial internet services were started in the US. Yeah, 2 of them in Virginia, UUNet and PSINet, and one in the San Diego area called SurfNet. So what happens, without going through all of the intermediate stuff, is that by 1991, Tim Berners-Lee sees this growing network as an opportunity to layer another capability on it called the World Wide Web. He invents the hypertext transport protocol, hypertext markup language, releases it, nobody notices, except for a couple of guys at the National Center for Supercomputer Applications who say, gee, wouldn't it be cool if we had a graphical user interface to this World Wide Web thing? And they built something called Mosaic, which makes the internet look like a textured magazine, formatted text and imagery, and eventually streaming audio and video. A guy named Jim Clark who was the founder of Silicon Graphics out on the West Coast, took one look at that and said, holy moly, that's a big deal. He brings Mark Andreessen, Eric Bina, and others from NCSA out to the West Coast to start Netscape Communications in 1994. It goes public in 1995, the stock goes through the roof, and the dot boom is on. All of the people who were interested in investing in internet threw money at anything that sounded like it might have something to do with the internet. So all this money goes in. The dot boom continues until April of something like 2000, and then there's a big dot bust. A lot of companies went out of business because they didn't have any income. They'd run through all their capital. But the internet continued to grow, and some companies that were founded around that time succeeded, like Google, for example, and Akamai in 1998, founded in the middle of the dot boom. So my story is really a simple one. I'm an engineer confronted with a problem. I had a colleague who was remarkably foresightful, Robert Kahn, and we had an enormous amount of help from people who were funded by various government agencies and who all wanted this to work. And I can tell you that the internet of today, while it is vastly bigger and more complicated and more capable than the one that began in the research world of 1973, still bears some of the early components of that design. And so my message to anyone who wonders how in the hell did you do this is I got a lot of help. And that's the first thing you should do. You want to do something big, get help, especially from people who are smarter than you are. The second thing I learned is you better learn how to sell your ideas, because if you can't do that, nobody's going to help you. And so those two things have really colored my story and have led to all of the recognition that I have received over the past 20 or 30 years.
Thank you, Ben. So Marty, you and the worms.
Wonderful, thank you, Susan. Before I go into the grisly details, I want to congratulate all the new physician-ears. I also really enjoyed going around talking to people at the posters. It's really amazing to see the enthusiasm, the excitement, and frankly, the ideas that you've all exhibited. So congratulations, and thank you for letting me be part of this. My story is a little bit different from the others you've heard. I was interested in science as an undergraduate, and I knew that if you were going to go on to a career in science, you should take a job over the summer working in a lab, get some real experience doing it. But I had a very bad idea. And the idea was that if I was actually supposed to grow up to become a scientist, I had to do it completely on my own. Asking anyone for help would be an admission that I didn't know what I was doing, which in fact was the truth. So I spent an entire summer working on a very nice biochemistry project, not asking anyone for help, and having the entire thing fail miserably the entire summer. At the end of the summer, I went to the man I was working with, and we talked about it. He said, look, you have 2 weeks before the vacation's over and school starts again for your senior year. Rest up, have a good time, go back home and everything. Come back well-rested and try the experiment one more time. And if you do that, then if it doesn't work well, then you're going to have to just drop it. But rest up and see what you can do. So I went home, had a wonderful time, saw family, friends, came back, and I did the experiment one more time, and it failed miserably. And I decided right then and there, I should never be a scientist. I don't have what it takes. I shouldn't do it. I had a wonderful senior year taking courses in all sorts of interesting things. Many years later, I got interviewed, and I said, yes, I took a course in Dostoevsky's novels. I took a course on 20th century drama. I took a course on 20th century constitutional law. But that sentence, when I was asked about it, got sort of changed I took courses in these subjects, which was true. And then a couple of years after the Nobel, I went to a meeting in Genoa, Italy, and there was a reporter, and he wrote up about this, having seen that sentence. And he wrote in his newspaper that after I failed as a scientist, I became a lawyer, an actor, and an authority on Russian literature. It was fantastic. In any case, I graduated from college, did a bunch of short-term jobs, and wound up actually teaching high school. And I made a discovery when I taught high school, and that was that high school students have summer vacation, and high school teachers have to find a job for the summer. And that's what I did, and I was very fortunate that a friend suggested, she said, I know this person who has a lab at Yale in the ophthalmology department. Why don't you go there and talk to him, see if you can work in his lab over the summer. And I went there, and he asked me, he worked on something I had never realized. I've asked lots of audiences this, so I will embarrass everyone here with this. He worked on the transparent part of the body and why it was transparent. And I've asked audiences this, how many people know what the transparent part of the body is, and asked people to raise hands. I won't do that here. But I can tell you that about 5% of the people in the audience do that, know what the transparent part of the body is. And then they say, and then I give them a hint. I said, well, let me help you. It's right in front of your eyes because it's your cornea. But we normally don't think about that. But we have been looking at our eyes our entire lives. But how many of you, and I certainly hadn't before I walked into that man's office, how many of us asked that question? Why is that tissue transparent? How can we actually see through this biological tissue? It's a fascinating problem. I loved it. He gave me a horrible experiment to do for the summer. I asked him a question because it vaguely reminded me of something I had read a couple of years before. And I think because I asked him a question, he hired me. I consider that the first miracle. The second miracle was 1 week after I started, he said goodbye, and he left to do his own research in France. It's 1970. There's no internet. He didn't want any letters. I was on my own, except this time I had people to talk with. And I found out there was another person who asked the same question I had. And I said, how would you test this? And we worked out a way of testing the experiment. And there was another person to show me how to actually get the experiment done. I had a lot of help. And so I tried this crazy idea I had. And it worked. And I can't tell you how wonderful it feels when you have a very stupid idea, but it turns out to be true. And you're excited about it. And all of a sudden, I really worked very hard that summer. I looked into all this stuff. The guy comes back at the end of the summer and he says, did you look at potassium? What happens? And I said, I didn't do your experiment. And he said, he was a little surprised at that. But then I showed him what I had and that I'd gone to a library and I had read stuff. And he said, oh, okay. And that actually gave me enough confidence that maybe going to graduate school, being a scientist, thinking about biological problems was something I could do. And I could get an immense amount of enjoyment from that. I'm not going to go through all the rest of my history, going through graduate school, doing a postdoc. But I eventually, what I do is I am a neurogeneticist. I work on a very small worm, as Susan pointed out, an animal called Cinorhabditis elegans. And I look for mutants that are defective in nerve cell development and also nerve cell function, particularly mechanosensation, which when I started, no one had any idea about the molecules that allow us to hear or touch or feel touch or any of a number of mechanical senses in our own bodies, how we detect blood pressure, for example. And so I was working with that. Clone genes. When you clone a gene, one of the very first questions you ask yourself is, what cell in the animal turns this gene on? And if this were the standard scientific theory, I would say no one had ever thought of that problem before. But that would have been such a complete lie that you wouldn't have believed anything I said, because we knew how to do that. There were really bright people that had come up with ways of doing this. So that wasn't the problem. I should also tell you, but we were interested in this problem, why or what cells turn on a particular gene. The other thing I should tell you about this animal is, just like the cornea, the animal that I work on, this 1 millimeter of an inch long worm, or 1 millimeter long worm, is transparent. We can look right through it. And one day, I'm sitting at a seminar, and I hear about the work of a Japanese scientist working in the United States, Osamu Shimomura, who his entire life was interested in bioluminescence, this fascinating aspect of biology where organisms can generate light chemically. And they do it in many, many different ways. And he devoted his life to this. And I'm listening to the seminar, I heard that not only had he found a bioluminescent molecule, a molecule that through the chemistry produced light, he found a biofluorescent molecule, a molecule that could absorb one color light, blue, and give off green light. And I'm sitting in the seminar, and it's just the very beginning, so I haven't fallen asleep yet. And I'm listening, and I say, I want to know where genes are expressed. And this, I've just heard about something I can use in my transparent animal. And I won't have to add anything other than light. I won't have to use fixed, dead preparations. I can look at live things and see where the genes are expressed or where things change in the cell. And I get so excited that I ignore the whole rest of the seminar. I have no idea what the guy talked about. I'm sure it was very important, but I just fantasized about all the things I wanted to do. And then I did the only thing that you can do in those circumstances. You get on the telephone and find out who's doing the real work. And I found that there was this person working on this, Douglas Pressure, and we set up a collaboration. Through some problems I won't go through because I've talked too long anyway. About 3 years later, we were able to show that all you had to do was put the gene for this protein, green fluorescent protein, into bacteria and then into worms. And a product would be made, and then you would put the specimen under blue light, and wherever GFP was made, you'd see green. And then I went off and worked on nerve development all over again. And fortunately, lots of other people use GFP, and that's what the Nobel Foundation decided to honor. I should mention one other thing. I did like organic chemistry as an undergraduate, but I wasn't very good at it. In fact, I may be the only chemistry Nobel laureate who has all C's in his college chemistry classes. It's not the grades, it's really the excitement about what we can do. And I'll leave with one comment. When I was inducted in the National Academy of Sciences, my, at the time, 12-year-old daughter came to watch the induction ceremony. And the ceremony is the most boring in the universe because 100 people are getting awarded but everyone in the audience is only there for their particular person, but they have to listen to everything. And as part of it, as everyone gets on the stage, a sentence is read about what they do, or why they were elected. And I realized that my 12-year-old daughter was going to be bored out of her mind. And so when I finally made my way back to where she and my wife were sitting, I thanked them for being there and sharing the time with me and supporting me in this. But I said to my daughter, sweetie, I'm really so sorry you had to sit through all of this. And my daughter looked at me as, frankly, she always looks at me like I am the stupidest person on the planet, and said, Dad, don't you understand about those people? And I'm going to say this to all the graduates, too, because it applies to you, too. I said, so what do you mean, sweetie? What do you mean about all those people? She had been listening to those sentences. She said every single one of those people was the first person in the world to do or see what they did. I'm exceptionally proud of that, and you now all have this opportunity to do that as well. Thank you.
Oh, thank you all for those stories of this magnificent mixture of curiosity and serendipity. It's wonderful stories. So for you, the graduating class of physicianeers, this kind of serendipity happens for these people, by accident and individually. But what we're seeing today is an emerging class of people who have been educated deliberately, intentionally across disciplines. I hope you understand that this has given you extraordinary power and flexibility. You're fluent in multiple languages and technologies in ways that, frankly, haven't emerged as a class of people before. And one of the things you've heard in all these stories is how important it is to have buddies in these processes, to have people to bump ideas off. So what we're going to hear about now, we want to talk about is this extraordinary possibility. So what do we see now as the frontier? How do we get there? And what are the promising frontiers of the convergence of disciplines? First, we're going to hear from Carl Wieman by video, and then we will follow up with, we'll start with Phil the next time and hear what other people have to say also. So first, Carl Wieman by video, please.
Let me first congratulate all you graduates, and I'm sorry I'm unable to join you in person. Now, at this event, you have lots of people talking about their Nobel Prize-winning work, but I'm not going to do that. Instead, I'm going to talk about the research I've been doing for the past 30 years on the nature of expertise and problem solving and how it's learned, and why that background makes me see this physicianeer program as an exciting educational innovation. Now, one of the most basic things we've learned about expertise is that people learn the thinking that they practice intensively. So if you want people who can bring engineering expertise to solving problems in medicine, you need programs where their education has them practicing doing just that, like this program does, rather than having them learn engineering or medicine separately and trying to then patch on the other skills as needed. It can be done, it's just not as efficient and usually not as effective. In addition, in our research, we've discovered that skilled problem solvers across the science, engineering, and medical disciplines solve problems in actually very similar ways. Their problem-solving process consistently involves making a standard set of decisions, 29 of them, including such things as what are the relevant concepts needed for solving this problem? What information is needed? How can I best obtain that information? And then how credible is the information I have and what conclusions I can draw from it, and a number of others.
Phil, do you want to pick up from there, please?
So if I take the first point that Carl made, it's solve a problem that requires convergent training and convergent thinking. And I found that to be between chemistry and biology, between biophysics and other things, a very, it's just part of what I am, and very productive. But for you, as graduating physicianeers, I'm getting better at that term, I want to charge you with something really, really hard. Medicine needs to be re-engineered. I'm talking about the whole healthcare system. The most powerful technology that's emerged in changing everything is information, data, and the effective communication of that knowledge and data and outcome to patients, to physicians, and to others. So 19% of GDP is healthcare. It's remarkably innovative, but it's remarkably inefficient. It's remarkably inefficient. You can't get a physician, you can't get in a room, you're scheduled in a hospital bed, you can't be moved out. It's remarkably inefficient. So re-engineer medicine and healthcare. It's something that's badly needed. It's interdisciplinary. It's really important to do. The second thing Carl commented about is really how to think convergence. And I want to translate that into a slightly different way. If you're going to be convergence in what you do, you have to be willing to expose your ignorance. You have to ask questions that you think are going to be very important to solve a problem, but ask questions of experts in which they know you do not have the knowledge to solve this problem. So if you're not willing to expose your weakness and ask people for help, you're going to be limited in what you can do in a convergence activity. Everyone wants to help. And if you allow them to help you learn and work together and learn from each other, you will be a highly innovative individual. So, and I can tell you, it's remarkably enjoyable because you make a friend, you solve problems, you change the world. So, I come from an institute at MIT where it's mind and hand. Take this physician engineering and change society. That's the charge. That's what Phil. Convergence is.
Thank you. And I think if we can continue Carl's video, another few seconds, I think. If not, we'll continue with the panel. Well, let's just see.
Now, while these decisions are common in solving problems across disciplines, to make those decisions wisely requires having the relevant knowledge, and in particular, having that knowledge organized so it can be effectively recalled and used in making those decisions. So I see unique value in a training program that develops these general problem-solving skills, including practicing and making the required problem-solving decisions, while providing the learners with the breadth of knowledge they need to make good decisions and effectively tackle problems that require knowledge that transcends our traditional disciplinary boundaries. Now, I assume your education has given you plenty of this type of mental practice. So in providing such an education, this is bringing together the cognitive components we see are required for a unique type of expertise. And so it seems to me that this program is doing just that. I'll close by repeating my congratulations and hope that all of you appreciate the unique cognitive capabilities you've acquired and will use those capabilities well. Thank you.
Thank you, Carl. So Marty, I thought I asked you to pick up now from both Carl and Phil, and then we'll ask Carolyn and then Vint. So you've confessed to a fair amount of ignorance.
Sure. So what I'm sort of struck with, what I'm excited about this program is going outside the normal comfort zone of what there is to study in terms of medicine. As I was thinking about it, though, the one thing that I think is you're not going to want to hear this. I'm going to say it anyway. This is really the start. I would predict that almost everything you've learned in terms of how to actually go about the manufacturing of things, or thinking about materials, or understanding the chemistry, or in fact knowing the bioengineering, all of that's going to change enormously. That all the tools that you've learned, the really important ones, as Carl said, are the tools of how do you approach a problem, how do you bring people together to try to solve problems. But it seems to me that the one thing that's really, there's two things that are really important, and you're right in the middle of them. The first is being able to acquire that new information. As we look in biology, which is the one thing I think I know a little bit about, that over the last several decades, there have been astonishing changes in what people could do, in how people think about things, and how people organize it. Parts of the cell that we didn't know existed are suddenly there. Our whole concept of what organisms are has changed dramatically. And it's not a real stretch to say that's going to change as well. So you need to find some way of sort of getting that new information to you. And that's a lifelong process, or at least bringing people together that will bring new perspectives to what you already have. And then I think the other thing that, as I was thinking about all this, I don't want this to sound like a criticism, but I think more a hope, is that I think sometimes as an outsider, medicine often gets described as diseases and as problems to be solved. And so I think if I have one wish for this class, it is to always remember that at the end of whatever process you're looking at or trying to make better, that there's patients, that there's people, and that are profoundly affected by all these changes that they're going through. And so I think there's this sort of pathway in my mind of going from basic foundational information to using that in unique and innovative ways to treating people. And I think that whole run is really very, very important. Thank you.
So Carolyn, you've had incredible courage in jumping into areas that were unknown, unexplored. So in this realm, so what do you anticipate that these physicianeers, what are the challenges that they're going to tackle that we could only dream of having solved for us?
Wow. Well, first of all, I should say that I've always learned more from students, I think, than they have learned from me. So in a way, I feel it's a little presumptive for me to be speculating for what your lives might look like or should look like. I would hesitate to even give you advice, because most of the advice I received when I was at your stage was really bad and didn't really relate to me at all, actually. So with that caveat, I will say, first of all, I've been really inspired by listening to Phil and to Marty and to Carl give us their wisdom. I think I've learned a lot from this panel already. And I think one of the themes that has come out from this discussion is the power of diversity. And diversity of disciplines, first of all, because the solution to impenetrable problems rarely comes from within that field, right? The solution often comes from left field. It comes from a place that you might not have anticipated. And the quicker you can bring together people from different disciplines, the sooner you'll find those solutions. For example, the solution to high throughput, low cost DNA sequencing came from the semiconductor industry at the outset. And I don't know how many people might have seen that coming, in the era of Watson and Crick. The solution to problems that we were interested in biology and medicine in my lab ended up coming from chemistry. And that happened because I had a diversity of people working in my lab, thinking from different backgrounds with different expertise and different mindsets. And so here you are, the first class of students coming from a program that has exposed you to lots of different people. And I imagine that you are the fabric that has connected your faculty from engineering with your faculty from medicine. I imagine that you are a node in a new circuit that has been created at your university. And I imagine after you graduate, some of your engineering professors and some of your medical training professors and physicians might continue to collaborate even after you've gone. Is that true? How many people here initiated a collaboration between two faculty that had never met each other before in your ranks? Any of you do that? Put your hand up. It's nothing to be ashamed of. All right, thank you. And I'm not. This doesn't surprise me at all, because I teach students too, and I see when this happens, and it's magic. So I guess maybe the important thing is that you've already learned the power of combining disciplines, medicine and engineering. And I'm hoping that another lesson that you've learned is the importance of having diverse people. Because at the end of the day, none of this happens without people. And I think all of us, can probably attribute some of the biggest moments in our professional lives to the gift of having worked with brilliant people who made it happen in the laboratory. And that's certainly true for me. And people ask me, how did you come up with these ideas? And, what was the backstory behind this research program that you can read about on my website today? And everything we do today, I can trace back to literally an individual person who happened to join my lab, had a certain interest and some ideas, and together something came to life. And had I worked with different people, I would have a very different research program today. And hopefully just as interesting and exciting, but different, because it was so profoundly influenced by just the individuals that I had the pleasure of working with. So never for a minute take for granted the people around you, each other, and the people that you will then train in your lives as independent engineers and physicians. So you'll be giving it back, you'll be paying it forward. And make sure that when you do assemble teams to tackle some of the big problems like re-engineering the entire healthcare system, that you build those teams with every vector of diversity that is available to you. People from different backgrounds, with different identities, who have different viewpoints. And good luck with that.
Thanks, Karen. And Vint, what do you see? What are your ambitions for this new class of physicianeers?
Well, first of all, I have to apologize that I'm supposed to be on a podcast literally 1 minute ago, so I'll try to be very brief. Most of the breakthroughs that I'm familiar with in interdisciplinary research often are the result of new abilities to observe and measure. If you can't measure it, if you can't observe it, it's very hard to formulate any kind of theory about why some particular process behaves in the way it does. And I would say that once you have observation and measurement available, then the next obvious thing is both inductive and deductive reasoning. And the power of both of those mechanisms is exactly the core that drives science. It's creating theories, making predictions, making measurements, and discovering whether or not the theories predict the measurements. And if they don't, first you investigate the measurement process to see if you messed up. And if you didn't, then you have a problem. Your theory didn't predict the right thing, and so you go back to the drawing board. My belief is that the graduates of this cohort will be walking into a world where observation and measurement and data collection and inference, especially with regard to pattern matching, is far more advanced than it ever has been. Although we hear a lot of Sturm und Drang and worry about artificial intelligence and machine learning, and while we have a lot still to learn to make those systems more manageable and avoid their hallucinations, they are incredibly powerful engines for discovering correlations. They don't necessarily understand causality, and that's where you come in. You have to have a model of causality to determine which of the correlations are relevant. But I anticipate over the course of the next decade that computational X for all values of X will be a core part of your future. And I certainly hope that you'll share with all of us the results of that enterprise.
Thanks, Vin. Thanks for joining us. All right, one last question, just kind of, and then we're going to turn to the students for their questions. So this is going to be a last question, and I just make this one a little bit more personal. We have talked a lot about the work and the process and all that, but I think one of the things that we find enormous, all of us as humans find motivating and actually rewarding, is that sense of joy that emerges sometimes, not every day. But I wonder if you could share with our students, several of your most profoundly joyful experiences in these amazing voyages that you've had. Marty?
Well, I've already sort of told that first experiment of having a silly idea and then actually seeing that it worked. That was wonderful. The first day that we got GFP to work and we actually could see it, and it said that there was no need for anything other than the amino acid sequence for the protein, was very exciting. But I have to tell you the truth, I get excited whenever I have an idea, no matter how bad it is. It's being excited about the idea. I'm not sure, I probably shouldn't say this, but I'm going to anyway. I think it's the poet W.H. Auden that said something to the effect of, everyone likes the smell of their own farts. I like my own ideas, no matter how badly they smell, and it does give me pleasure to read a paper and suddenly say, I wonder if this applies here. I wonder what this means. So it's a much more general thing, but those are the things that I like doing. I like when that connection is made, and I feel that that's what you're all about to be doing, or have already done, and are about to be doing even more.
Carolyn?
Well, there's so much joy in this profession. I wouldn't even know where to start. I mean, there have been moments where a student had a big result and came running into my office with the data to show me, and with a big smile on their face, and I just swelled with pride and joy. So I've had many moments like that. But what comes to mind in this moment is the fact that just last week we had the 10-year anniversary symposium for an institute that I moved to Stanford back in 2015 from a previous job at UC Berkeley to help launch. And so in 2015, this institute we built was just a twinkle in the eye and a kind of pretty sketch on paper. And I think the mission of the institute will resonate with this group. The acronym for my institute is CHEM-H, Chem-H, but but that actually stands for chemistry, engineering, and medicine for human health. Okay? So we at Stanford have been trying to build an institute, a research presence, and training programs that are, I think, very much in line with and have a significant Venn overlap with this group, physician and engineer with the scholarship in the intellectual discipline of science, above it all. And last week we had a symposium to celebrate our 10-year anniversary where I got to introduce the 17 new professors we hired, over 100 graduate students that are training in our kind of version of this program, but for PhD students, as well as post-baccalaureate students and undergraduates in a new major, and so on and so forth. And I sat there and I just felt such pride because I felt like, me, this one person, did something at a university to try to make a difference. And there was like a tangible evidence of that in this symposium. So that gave me personally a lot of pride and joy.
Thank you.
And I imagine Rod is probably feeling very similar right now.
Phil.
I agree totally with Carol, and that there's so much joy in an extraordinary profession that we share in being an educator, a researcher, a professor in an academic world. To pick out a couple, I get immense joy when someone who's trained with me goes out in the world and then comes back and tells me something that I think is spectacular. I just didn't understand this, and you're telling me this, and it's expanding men's, women's knowledge and ability to make a difference in the world. And that's a remarkable experience. The second remarkable experience is when you're at a dinner or a party and someone sits down beside you and we start talking and they understand that they have a loved one who's been treated with a drug that has come from your activity and your research. And they look at you and say, thank you, all right? And it's what we leave here is what's important. What we help others is what's important. And that's where I really get a lot of gratification. But I can tell you, this is one of the most remarkable careers one could have in contemporary society.
Great. Let's thank our panelists for an incredibly insightful set of. All right, they're not done working yet for all of us. We're going to turn to our student questions. And I'm not sure how those questions are going to be delivered. All I can see are these very bright lights in the back of the room. But we have, I think, plenty of time to get some questions from the students. And where's our stage director who can help me understand from whence these questions will come? I'm sure there will be wonderful questions from these brilliant students.
We just need a mic.
We need a mic, yeah.
There is a mic.
Okay. There we go. Thank you. And if your questions are pointed to some particular person on the panel, just you can just indicate that. And if they're general, indicate that. We will all do our best.
Hi, my name is Kenneth. Thank you all so much for this panel. This has been wonderful. So my question is just along the lines of coming up with ideas and vetting them. Dr. Chalfie, you mentioned that you have a lot of ideas, and so I guess I'll direct this question to you. So I'm imagining myself as a busy resident, and I'm have all these ideas, things I want to do, not a lot of time, not a lot of money. And so, what is your personal vetting process when you have these ideas and determining whether something's worth putting time and money into it? You have like a systemic process you go through, or that's just kind of curious how you attack that?
I'm sorry to say that I don't have a particular process that I look through. I probably get excited about way too many things, and I really enjoy talking with people about them. We have a journal club that we have in the lab. Francis Collins is here. Francis gave me this idea from a journal club he used, which was to have a journal club of papers from bioarchive, something that had not been published yet. And I started that in my lab, so everybody in the lab reads the paper. And I think by now the people in my lab are very annoyed at me because every single time we have the journal club, whatever the paper is, there's at one point in the afternoon when I say, okay, so how can this apply to what we're doing? Because it has excited me in a direction that has come that sort of out of the blue from the paper. So they're now prepared that I'm going to ask this question, and they think about it too. But to me, that doesn't. But you're asking a different question, which is, how do we evaluate, is it a good idea or not? And that's a very difficult one to change. The wonderful Nobel Laureate who died several years ago, Oliver Smithies, used to talk about a weekend experiment. The experiment where you just have this idea, you got to try, but you're too embarrassed to tell anyone that you want to do it. So you do it on the weekend when no one else is around. And if it works, you crow about it Monday morning. If it doesn't work, you simply ask people how their weekend went. But the idea, I think that unless it's something that takes an enormous amount of resources, I like for myself and I like for the people in my lab to have the chance to try, to just experiment with it. If something comes up, wonderful. If it doesn't, you go on to something else. But that's about as much of a process as I have.
Anything? Next question?
I've always tried to find an expert in the field that's associated with my expertise, whose opinion could be enlightening about this idea, and pitching it to them and seeing if they look at you with this, or they look at you as that's interesting. And it's the equivalent of taking your idea in the marketplace and finding out if somebody will salute it. And the counter is having a new graduate student and seeing if you can talk them into doing the experiment. and if you can't, then it's not a good idea. But if you can, after several tries, then it gets tried.
But, yep. Yeah.
1 second. That shouldn't be done in the sense, I can tell you that after we found that GFP worked, and I was profoundly excited about it, nobody in my department, except for one person, saw the usefulness of it. Later they did, but at the beginning there was only one person who actually did the next important experiment. We showed it could show where genes were expressed. This person showed that it could show where proteins were made and distributed. I'm particularly proud about that. I had nothing to do with the experiments. It was done by my wife. She was the one that realized the importance of using this as a tool and developed it beyond what I was able to do. And it was very important. But I'm a little bit hesitant about making sure everyone thinks it's a good idea. Yeah. Try it. Sorry.
Okay, I'll try and bridge the divide here because I think ideas come from many places, right? There's a diversity of places from which we craft ideas. Sometimes it comes from within, and like you have conviction. You know it's important. You have conviction in the face of, disagreement. And sometimes people are downright, I think they look down their nose at the idea. And I've certainly found myself in situations where I had conviction something was important and should be studied, and had a hard time convincing anybody that it was important. So I know what that feels like. I also know what it feels like to have the problems come to you from subject expertise, especially doctors and patients. We started working on a rare disease in my lab at Stanford, which I had never heard of and probably never would because it's very ultra rare. But it turns out there was a little girl diagnosed at Stanford Hospital with this genetic condition, and she was the first patient discovered to have this genetic disease. Now there's maybe 100 or so patients that have been identified around the world. It happens to be a disease in the area of glycobiology, which is a subject that my lab has expertise in. And so the father of this girl found me, did a Google search, I guess, and they were at Stanford, I was at Stanford, and he cold called me to ask me if I would work on this disease because it was brand new, no one knew anything about it, his daughter was sick, and he was a desperate parent. And that's a compelling source of an idea, okay, to work on. And you have ideas like this yourself. For example, I was really impressed with the posters in the back from the team that is trying to make a better hospital gown for ambulatory patients, because this is a problem that any patient, or most of us, have experienced. I mean, whose idea was it to make a hospital gown that just falls open in the back when you're walking down the hall to the bathroom? That's horrifying. And so thank you very much for your service. I really hope, I hope that gown gets picked up, because that would be much better. And that's an example of a problem that I imagine came from patients, and which includes all of us at some point in our lives. But baked into your original question was, you're a busy resident with no time and no money, you have ideas, but how do you actually execute them? And that is a problem. And I think as you're re-engineering the healthcare system, maybe you might also do some work on the experience of the resident, of the medical resident. And I can tell you at Stanford, we hear our own residents talk about their frustrations, not having the resources, the bandwidth, the time, the space to actually try to develop an invention and implement it in the clinical space. And so we've tried to create some programs that liberate residents so they have some time to devote to a research interest. We have seed grant programs so that they can team up with a scientist that has a laboratory and try to get a little bit of money and some hands in a lab to actually work on the project. And I hope it can make a difference to our residents. It would be great if a program like that could be scaled and that you would be able to avail yourself of that kind of an opportunity.
Yeah, thanks. Next question, and actually just line up. I don't know where the questions are coming from, but please, go ahead.
Hi, my name is Amelia. It's such an honor to meet all of you and speak with you. I had a question kind of as I was sort of listening to all of your amazing stories and hearing, I think, a very common theme about how important it is to be surrounded by people who are supportive of your career and your dreams and all of that. And I find that my classmates and I, as we're moving into the residency role, are going to be, I think, in the professional setting for the very first time, like mentors. We're going to have people who are actually looking up to us in a professional setting, namely medical students that we start to work with. So as I was kind of reflecting on that, I just kind of wanted to hear if any of you have any lessons you've learned along the way about mentorship, and not only how to be mentored, but also how to begin to step into the role of a mentor and how to do that in a way that's supportive of folks' hopes and dreams and goals. And I'd love to hear from you about some of that. So thank you.
Thank you. Let me just start on that. I think one of the things that's hard all the time, but certainly when you're starting out, is to give an answer fast. And one of probably the most important lessons for me in learning how to be a mentor was being a really great listener. And particularly when you're in a hierarchical relationship, which you will be, and you're going to be on the top side of this hierarchy, it's often hard for the people lower on the hierarchy to speak to you fully. And so giving your mentees enough time and space to get the idea out and help their idea get better through your questions, without the reflex of saying, oh, no, that's a bad idea, right? Which is kind of often our first response. But the first response is, well, tell me more, perhaps. And, as I said, it's a lesson that took me a long time for me to learn.
Just very quickly, I always liked the wonderful way that Ed Kravitz, a wonderful neurobiologist, would start his seminars. He would always start them by saying, when I say we, when I say I mean we. And when I say we, I mean they. And that's a good perspective, I think, in all of this is, and frankly, and I think this has been said before, one of the things that's really wonderful about working with the students and postdocs and other people that we have in the lab, for me, is the collegiality. The fact that it might start off as a hierarchy, but it very soon turns out to be a collaboration. And those are the most fun, when it really is a collaboration. And as Carolyn has said before, everybody learns from everybody else, and we continue doing this. And I think that's a good perspective to stay with as you go on to be in these other sorts of positions.
I'll just say one other thing. I think to be a good mentor, you've got to be willing to allow a mentee to fail. You can tell them why you don't think it's going to work, why you don't think it's important. But if they stand there and then listen to all of that and argue with you, the most important thing you can do for that mentee is make them responsible for their ideas. That's the most important thing you can do. And get them to stand up for their ideas and give them space to fail. And not in a harmful way, but in a learning way. Support them and then bring them along, because identifying the problem, committing to the problem, and taking responsibility to make it work is really the most important trait you can have in science.
Other questions, or Carolyn, whatever?
Well, first of all, I mean, the three people sitting here with me are legendary mentors. They've produced legions of incredible scientists who've changed the world in ways that have just amplified their own contributions. So that's one of the really amazing, beautiful aspects of mentorship is that it's important in its own right, but it also gives you the opportunity to make change at a much larger scale than a person could do on their own. In terms of mentorship, I think I've made all the mistakes that people make when they're new into the role of a mentor. And I've both been I've made mistakes as a mentor, and I've received bad advice, right? So you learn from all of this. And those learnings have taught me that, first of all, I think you need to mentor people as individuals, which means you really have to understand a person and what drives them and what motivates them and what their hopes and dreams are. In order to be the most effective mentor for them. So I think investing in the personal relationships with the people that are, in your group of mentees is very important. And I made the mistake early on in my career of just treating everybody like clones of me, which none of them are. Then there are other sort of mantras in my mind. For example, I'd like to think that if one of my students is excited about something, then I'm excited about it too. Right? If they're enthusiastic about pursuing something, then I'm enthusiastic about it, and I'm there to be their partner in that endeavor. I always thought of myself as a supporting cast in my lab, not the lead role. And I think that's helpful as a mentor, is to understand your role as a supporting cast member. And at the end of the day, I think it's about respect. If you respect the people you're working with, and with all of their differences from you, and their different goals and their different ambitions and their different priorities in life, as long as you understand them, support them, and respect them, I think you're on the right path.
Other questions?
Oh, great. So first of all, I want to thank you guys for, giving us a chance to listen to some of the intellectual titans of science over the last 25 or 30 years. And for these new students moving forth into their fields, it's going to be phenomenal to kind of follow in the footsteps that you guys have presented to them, and also getting a chance to interact. But my question is really for them as they're looking for the next 3 to 5 years. What do you guys see individually as the biggest breakthroughs that you think are going to happen either within your space or within the surrounding field that they can expect to happen? I mean, obviously what we're seeing with artificial intelligence, it's been phenomenal. The breakthroughs that are happening in medicine right now are coming at an absolute breakthrough pace. I mean, it's just happening so fast, it's hard to kind of even manage all the data information that's coming at everybody. But what do each of you guys see as what the biggest thing that you think is going to happen that's going to change their lives as doctors, and what to expect? And I know it's a pretty big thing, and everybody has a different thing. I know the guys at Harvard and MIT think one thing, the guys at Stanford think of one thing. Everybody's got a different thing they think is going to be the big game changer to expect. But what do you guys think?
Phil, want to start?
I'm going to say something that probably everyone will consider obvious. The impact of AI and machine learning on biological and biomedical science is something that's mostly in our future and is going to be remarkable. So sustained, long, 25 years, lots of dynamic change.
Carolyn?
I agree with this for sure. In fact, I tell my students that if they should start learning, acquiring some computational skills, and so that they can at least understand what the impact could look like, if not practice it themselves. So I agree with that. I think another important change that's underfoot is the participation of people in science that historically were excluded. And I think the doors are finally cracked open for people to get into science and engineering and medicine who were locked out for so long. And what that means is that I think the problems that we will hopefully be tackling, as people interested in human health, will change the lives and improve the lives of much more people. People who can't afford current innovations, that can't avail themselves of these remarkable new medicines that have become available over the last 5 years or so, gene therapies and cell therapies and genetic medicines, still are not available to most people, even in our country, much less the world. And so, I would like to think that there's finally a reckoning with the fact that because of the economics of healthcare and the way that we deliver it, we leave most people out. And the more people we can get into the sciences, engineering, and the medical practice, I think the more aware we will be of how important it is to make medicines and create technologies that everybody can access.
I don't think there's anything I can really add to this. I think that we're in the middle, certainly, of a revolution in terms of genomics. We have been for a while, but we're nowhere near towards the end of that. That's going to profoundly change how we look at ourselves, how we look at each other. And there's an aspect, to build on what Carolyn said, of the global nature of health. I think if there's anything we've learned from the last 3 years, it is that we cannot think parochially about health issues, that we really have to be thinking globally, not only bringing techniques to people, but to be able to understand really humanity in a much broader sense than we've ever really looked at before. And I think that's going to have some profound changes on us.
Yeah, so I'm going to repeat something that I said earlier because I think I agree with everything everyone said. And to Marty's point, biology is exploding. And when we think about biological systems, they've evolved to be incredibly efficient. And these are going to be tools that if you think about applications that may be different from how a particular biological solution is used in nature, the opportunities are vast. So I love bringing the engineering mindset to the exploding opportunities in biology. If you're please. And thank you for coming to the front microphone. I don't know about everyone else, but I couldn't see you at the back one. So please go ahead.
So firstly, it's, I've never been exposed to such brilliance before, so this is pretty inspirational. But I'm obviously much younger than the rest of the audience here, and I'm curious to know what things. I actually just graduated high school yesterday. So
Congratulations.
Thanks. Not as impressive as all of these guys, but close.
Not yet.
So yeah, I'm headed to college in the fall. And I'm curious to know what things in your all's undergraduate education was like most impactful to your successes. What things did you really appreciate doing? What are some things that you wish you did that you didn't end up doing? Stuff like that.
Can I just want to start because there was something that happened to me when I was in college that changed my life. No one told me, and I didn't know, that the faculty were there for me to visit. I've been a freshman advisor at MIT for a while, and what I tell my freshmen is the faculty would love to talk to you, but they won't talk to you unless you talk to them. And it was very late. It was my next to last semester in college, and I had a fabulous course. I went to talk to the professor because I was curious, and he basically told me what the direction of my life should be rather than the direction I was on. So, I mean, I owe him everything that happened. But I didn't know to have that conversation. I didn't know. So avail yourself of not just faculty, but I would say mostly faculty, and to just express your curiosity. Go to them with questions, and you will learn things that you couldn't imagine that you were going to learn.
So this is in the realm of, this is advice that happened to me but has no bearing probably on anybody else. The thing that I found most, as I think back about it, most profoundly affected how I think when I went to college were all the courses in the humanities and social sciences that I took, not the science courses. And it was, yes, we solved problems in the science courses and everything, but what was really striking about the social science and humanities courses is we'd read a ton of material, and then there'd be that final exam, and the final exam would ask a question that had never been asked before, and you had 3 hours to scramble to manufacture an answer out of thin air from whatever you had read. BSing is what I learned in college, but that's a profoundly important part of being a scientist, as I've brought up a couple of times. You want to be able to draw your ideas from all sorts of places and put them together. And I think it was those final exams in those courses where I was sort of taught, take these various parts and make a story from them. Make a hypothesis and build it up with whatever facts you can present.
Phil, Carolyn, we don't have to all answer everyone.
I have mentored, advised MIT freshmen for 45 years. My words to them is, find something you're passionate about, be as good as you can be in that subject, and don't compete. Because there's always going to be someone at MIT who's better than you. So find a group of friends to work with, become informed, learned, and action in that field. And you'll come out of MIT in a place that will be a springboard for a life of learning. And I think it's true of any other place.
Where are you going to go to college?
I'm actually going
Well, making a point.
Maybe I'll have one of you guys as my advisor.
Okay.
Do you know what you're going to study yet? Have you thought about that?
Yeah, probably computation and cognition.
Oh, wow. All right.
Well, the 6,
We call that 7-9.
Yeah. Well,
No, sorry, 6-9.
Okay.
6-9.
Whatever number 7.
Well, then I'll tell you this. One thing you should learn, and do your best to challenge yourself and put yourself in situations where you're forced to learn how to write.
Yes. Yes.
Writing skills, yeah. I can't tell you. And maybe at MIT nowadays, there's a whole host of humanities classes where you have to write 20-page papers and 30-page papers and so on. I don't know. But when I was at your stage, graduating high school and figuring out where to go to college, my dad was a professor at MIT. Okay, he was in the physics department. And he wanted me to go to MIT because it would have been free. Okay? And instead I did the worst thing a person could possibly do, which is I went to Harvard, which is like 1 mile away and not free, okay? But one of the reasons I did that is because I didn't know at the outset whether I would want to be a science major or maybe major in a humanities or even music. And Harvard had more different majors available at that time than MIT did, which was very much science and engineering at the time. And at Harvard, one of the pain points for me was because I had to take a lot of classes in literature and sociology and political science and all these other humanities subjects. I had to do it, it was required, regardless of your major. I had to write and write and write and write. And boy, did I complain about this. And this was before word processing. I had to do this on a typewriter with whiteout, It was really hard. But by the end of those 4 years, I finally learned how to write. And I really hadn't learned in high school. I was not a good writer. And so then later in grad school in chemistry at Berkeley, I had an undergrad working with me. He loved chemistry. He was a brilliant undergrad. And I said, hey, what led you to chemistry as a major? Is it just because it's so amazing and you're so good at it? And he said, no, to be honest, I don't want to deal with people and I don't want to have to write. That's why I wanted to be a chemistry major. And I thought, oh, you're in for it, man. Because guess what? All you're going to do as a chemist is deal with people and write, believe it or not. And so I forced him to write, and he co-authored some papers with me, and he had to write the draft, and I just took this guy down to the mat in writing. So you're going to MIT, you're going to be in computer science, plus whatever. Maybe they won't force you to do a lot of writing. That would be a travesty. I don't know what it's like there, but when you get advised by Professor Sharp here, make sure that when he tells you, sign up for all these writing courses, that you do it and you take it seriously. Because if you learn nothing at MIT other than how to write, you're still ahead of most of your classmates.
I would say you have drop-in rights for 2 faculty at MIT now, so we'll see you on campus.
Thank you all very much. Appreciate it. Thanks for the insights.
All right. I was actually really excited to ask a question written by ChatGPT, but after lots of prodding, there wasn't really a good question.
You still have to learn to write.
Oh, yes, exactly. Yes. Well, it didn't do a very good job, despite all the revisions. So I was actually inspired by one of our graduates, I think it was Amelia, and your thoughtful responses about mentorship. And I was wondering if you would share maybe the most challenging piece of advice that you received, something that was really hard to follow and that you thought was really helpful.
This one is called Stump the Panelists. Okay.
Sorry, is the question what was bad advice that we got? Or?
Well, no, optimally, like good advice that was really challenging to follow, that you either thought was counterintuitive or useful later.
Oh, that's a good one. I can tell you some bad advice I got.
Sure,
Maybe
yes.
that's easier. When I first joined the faculty at Berkeley as a brand new assistant professor, many people told me, you need to have a strategy to get tenure. And you should make sure whatever you work on is going to get you tenure. That was horrible advice. Nobody should do anything because of tenure. That's just a complete, that's an artificial construct that has no value in terms of what you do to help society. And so to the extent that a person is focusing on something like that, when really they should be focusing on like what knowledge can I create, what inventions can I realize, and gift those things to the world. And then either you get tenure or you don't, but that's really not the point, I think. So that was bad advice.
So I will make a comment here. In 1978, when I got involved with Wally Gilbert and a number of European scientists to start a biotech company called Biogen, I got frowned down upon by most of my biological colleagues. And it was the worst advice they could have given me. Because it gave me such a much broader view of the world and a way to impact society in a positive mode that it would have really been a loss to me, a loss to society, because I'm much more effective because of that experience, and just a meaning in life because I was able to contribute to other people through that vehicle and be a better mentor at MIT. My first love was research at MIT. That's where my anchor was. But having that external experience, being involved in entrepreneurship was a very important part of the experience.
Any examples of someone giving me advice that turned out to be bad because I ignored so many people? So or at least I've repressed them all. It wasn't so much advice. When I went through graduate school, there was much more a feeling of hierarchy. And I think that's been around. And it wasn't so much advice, it's that I accepted it. That there were people that were just mean. And I didn't speak up, and I should have. And I think that we now have a much better, or we're beginning to have a much better idea about what's appropriate and what's not appropriate. And I think that the bad advice was I was too intimidated by a feeling that there were people that were in authority. So it's not really advice, but it was occurring, and I think it was very inappropriate. We're not talking about horribly gross things. It's just that people had power. They still have power, and I think we need to call that out.
I would just say that happily, I'm a little deaf in ways. And there were a lot of things that people told me not to do. And being a little deaf, I went ahead and did them. And it's a hard, so I think my advice is you'll get advice, and you don't need to follow it. But I think it's always a good idea to get advice from a lot of people, but you're going to have to, the important thing is that you make the decisions for yourself. And there were many things that I decided to do that were completely non-canonical. And I got many cautions that it was going to wreck my career. And, but at some point, there are things that you'll know that you want to do and that you have to do. And I just encourage you to be courageous, standing up for people who are being treated badly, pursuing experiments that people say are stupid. Starting alternate careers or taking divisions to your career which are not common routes to take. Those decisions are up to you. And there's no guarantee that they're all going to work out well. I guess the important thing is to have an escape path.
Hi, my name is Shoria. Thank you all again so much for being here. It's really inspiring and an honor to have you guys. My question is, I just feel so curious about novel technologies and just a whole variety of different fields that are constantly emerging. I know artificial intelligence was just mentioned, and then just across every discipline in engineering and medicine. But at the same time, we're being told to, find one passion and stick with it and pick a lane. How do we do that when everything is so exciting, and then maintain a level of focus to become a Nobel laureate one day?
Yeah, I just want to say, I don't think any of us have advocated that you find a passion and you stick to it, because your passion will change. Ours did, I'm sure, along the way. And
right.
I would not be committed to something just because you were passionate to it last month. I'm passionate for it last month. But I have to tell you, maybe 1% of the people I know, many of whom are enormously successful, knew who they were going to become at the outset. There are some small number of people I know who have done that, but most people I know have just kind of, stumbled along from one interesting thing to the next, and follow your passion as it evolves.
Sure.
I think is really the advice that each of us would give. And those curiosities, those interests, those enthusiasms will lead you in directions that you could never imagine at the outset.
So I think it's the wrong use of phrase. I think one of the things we do whenever we see talented people, as all of you are, is we want you to succeed. And so we say, follow your passion. I can tell you for myself, and I suspect some of you still feel this too, my inner voice says, tell me what my passion is so I don't make a mistake, that I didn't pick the wrong one. And that's not what we're saying, that there's one thing you're going to do that's going to allow you to succeed or anything like that. I think, I'm going to try to put words in everyone's mouth, but I think what we're really saying is be passionate, be involved, be committed to it. Don't go in halfway. Be fully devoted to what you want to do. And it might not be the thing you're going to work on for the rest of your life, but you will have had the satisfaction of really going after something, and then you go after something else. So it's not what is my passion and now I'm stuck with this thing for the rest of my life. It's how should one approach all these activities. And what we're sort of saying is full-throated, complete, as complete as you can, not a halfway measure.
Thank you.
We'll take these last two questions and then we'll
Hello. Thank you all very much. My name is Jihan. I'm actually a resident in the neurology department here. And one of the questions I wanted to ask y'all, from somebody doing research, from trying to be an innovator as a resident and facing a lot of the
We're having a
problems.
hard time hearing you. If you could just
Sorry,
get
yeah.
closer to
Oh,
the
it's
mic,
even
please.
better.
Thank
yeah.
you.
Hi, I'm Jihan. I'm a resident here. And one of the questions I wanted to ask to see y'all's advice for them, for their new graduates. As a resident, as somebody who does research, as somebody who tries to innovate, one of the unexpected roadblocks that I've come across and that I still don't quite know how to address or deal with is the limitations imposed on development and on the ideas and on the advances I'd like to make that come in from things like commercialization, from intellectual property protection, right? There's this, a lot of those things that we've talked today about sharing our ideas, about, finding a passion and taking it out there and sharing it with the world and doing something better, but a lot of that comes into direct head-to-head conflict with commercialization, with tech transfer, with things like that. So I wanted to know if there's any kind of way, any advice you might have to prepare them for how to deal or how to prepare themselves for that sort of thing, if that makes sense.
Phil is well positioned to.
So Of all the, out of, let's say, 10 situations where someone is trying to take a new idea that they think has real value and get the resources to execute on it, I think the most limiting aspect of it is to be secret about it. You've got to go out there, tell people why it's important, see if you can get them excited about it, and get resources and people to share and work with you to make it happen. Ideas have a short half-life. So if you're actually going to be able to make something happen, you're going to have to be open and move and get people to join you.
All right, one more.
Thank you.
Go ahead.
Sorry, I'm short. Hi, it's an honor to be able to listen to you today. Thank you for your time and for your insights. I was wondering if you would be willing to share what some of the most challenging things you faced in your career were, and what advice do you have to young scientists when they face similar or just very large challenges in their careers?
So I'm just going to describe one. So I got a grant early in my career, and at a point where was surprised I would get it. And I thought, with all the work I had done, the renewal was in the bag. I was at a place where if you didn't have grant funding, you didn't have anything. I was at the Cold Spring Harbor Laboratory, and having a grant was essential. And the grant did not get funded. And I did something that I'd never done before. I reached out. I called people. I talked to people. And the ideas came forward. I got really good advice from a program officer at the NSF who gave me advice on how to reposition the material. I ended up applying for 2 grants and got them both. So it ended up happily. But there was this moment of just doom. I mean, things were just over. But it was this reaching out, talking to people, asking questions, to expose yourself. My grant wasn't renewed. That's an embarrassing thing to say. In times of crisis, the last time you actually imagine talking to anyone, that's the time when you need to talk to people.
I can add something if there's time. I know that we're in a time constraint, but
yeah.
For me, I already alluded to this. I think the biggest challenge was in the early parts of my career when I was trying to break into a field where the dominant culture was one that would presume I was not capable of being an organic chemist. And so trying to convince people that someone like me, who's female, I'm also gay, and I was an out gay person, in the late 1980s, this was pretty stigmatized, and convincing people that they should look past their biases and give me a shot. And one thing I learned during those early days was that you might think you want to do something, and there might be a lot of roadblocks, and they're artificial and unfair, and they lock you out. But it's almost like you're sitting at a bus stop, and buses come by, and those buses are opportunities. And it helped me to develop an instinct so that when I couldn't get what I really wanted, at least I was able to recognize opportunities as they came by, and sometimes the bus door would open, and I was like, okay, it's not what I had in mind, but I see an opportunity, and I'm just going to get on that bus and go.
Yeah.
And so that was very important early on, because although I wasn't able to do organic chemistry for many years, I found my way into a physical chemistry lab, and so I was a physical chemist for a while. And then I was doing computational work for a while. And it took many years, but eventually I did find a crack in the door to get into organic chemistry. And the interesting thing is I had all these other experiences which weren't kind of top of mind, but they were opportunities that actually were really good for me in the end. And so I think it helped me to understand that sometimes you can beat your head against the wall and you just can't break it. But if you look to the side, you might see an opportunity, unexpected, and just get on that bus and see where it takes you, because it's better than getting stuck in place.
Mm-hmm. Thank you. And I'm sorry, we've got Peter Agre waiting, and so...
I just had one quick question.
Okay, one quick question.
Here we are in the largest medical center in the world, can you each give us one idea on how to make the medical system, our healthcare system, work better?
Well, that's a really short question. I'm not sure we have any short answers. And my answer is, these are the people. Well, our answer is them. All right. We now want to welcome Peter Agre. Peter, it's so great to see you, and thank you for being able to join us to offer some valedictory comments. It's wonderful to see you, even if by video.
Thank you, Susan. I'm sorry I'm not there today. I was in Houston with you 4 years ago when the EnMed program was launched. And those 4 years, they went by fast, but they were pretty tumultuous 4 years. Coming out the other end, you must be looking back and thinking that this is probably the most stressful time to be a medical student since World War II or 1918. It's been something that the country didn't expect, and we discovered some glaring deficiencies in our healthcare system. And one of them is the dire need for physicians who have backgrounds in engineering. The computer dashboard system was something produced by healthcare workers working with engineers. The modern development of vaccines involved health and chemical engineering. So I think that you've come along at the right time, and I congratulate you for that. I just have a few kind of lessons of life I'd like to share with the students. I'm a father and a grandfather, and I learned a few things, and I will start by answering a question one of the students posed. Dr. Agre, how did you theorize the existence of aquaporine water channels? And the answer was humbling. We had no idea there were such things as water channels, but we were studying red blood cell membranes and the rhesus blood group antigen, and we stumbled upon a protein that had not been identified before because it didn't stain with the typical protein stain. And it was very abundant in red cell membranes, but we were clueless as to what it did. Now, Marty Chalfie made, I think, a very important point just a few minutes ago, that you should not be secretive. I mean, there's always a possibility that you'll give away information that should allow competitors to scoop you, but when you have no idea what the importance of a problem might be, I think sharing it is a very good idea. Now, the reason this has family significance is because as a basic scientist on a modest income, we knew that every year our vacation would be in a tent. And Mary, my wife, is very interested in nature, and so we went to the national parks, Yellowstone, Glacier, Smoky Mountain National Park, and we did this for a few years, and the kids loved it. And then Mary said, we should ask the children which national park they want to go to next summer, and they all yelled Disney World, which is not a national park. But we went to the Everglades, and then we went to Disney World, where they saw the difference between real alligators and Disney alligators. And the long drive back to Baltimore, we stopped in Chapel Hill, North Carolina, where I lived for 3 years, where our oldest child was born there, and we had friends and colleagues. And it was sharing the story of this 28 kilodalton protein we discovered, the mystery protein. And it was a conversation with John Parker, an elegant hematologist who was also running a physiology laboratory, who put his finger on the right idea. He said, Peter, this protein is abundant in red cells and also in renal tubules. Have you considered this is the long-sought water channel? And that's the first time I heard those two words together, water channel. And at John's suggestion, I did a lot of reading and teamed up with Bill Gugino at Hopkins, and we demonstrated that this is the first molecular water channel known as aquaporin-1. And this led to other things, but it really, the theorizing that the aquaporin water channels exist was something done by others. And by sharing information, we were put on the right track. And I'm forever grateful to John Parker for making that suggestion. I think we often need help of others, and we should not always take ourselves so seriously. I've often been asked, what was it like to be informed that you receive a Nobel Prize? And it happened by a phone call early in the morning, 5:30 in the morning, October 10th. The phone rings, and there was a pleasant voice on the other end. This is an important telephone call from Stockholm for Professor Peter Agri. Are you Professor Agri? And I said, I sure am. And he explained I would receive the Nobel Prize, and I was delighted. And then they said that in 10 minutes we're going to have a press conference, and you should get ready for your day. So I sprinted to the shower and was getting ready, and my wife, Mary, called my mother back in Minnesota. My dad was a chemistry professor, but he had died 8 years earlier. And Mom, a widow, was living alone at a retirement home. She listened quietly as Mary explained the Nobel Prize, and Mom was a farm girl. She never had the opportunity to go to college. But her response was very interesting. She said, Mary, tell Peter that's nice, but don't let it go to his head. We're still waiting for him to do something useful. I think she was thinking about EnMed. Engineers do things that are useful, and that's what makes science so important. So I think it's important to, in addition to working hard and conferring with others, to make time for your family. I wasn't always very good at that. Our daughter, Claire, we have 4 wonderful children. They're grown now, and we have grandchildren. But when Claire was about 8 years old, she was in a children's theater program called Pumpkin Theater, and they would work on a Christmas program, and the parents were all invited, and I was struggling to get my first grant renewed, and when I was invited, I said I'll try to be there. But as it was on a Saturday afternoon, and as things were working out, I worked past the time that I could see and Claire in her program, and I arrived home, and I noticed that she was sort of sulking in the entry hallway, and I explained that adults have responsibilities, and sometimes they just have to put family aside because they're too busy. And Claire listened, and she responded by saying, but Kathy Schmoke's father was not too busy, and he's the mayor of Baltimore. I have had other experiences reminding me that family really deserves to be at the top of our interest list. Now, as physician engineers, you're going to have unique opportunities as physicians to take care of patients, as engineers to use that information. And I'm reminded of the brilliant saying of the American poet Maya Angelou, who said, I have learned that people will forget what you said, people will forget what you did, but people will never forget how you made them feel. As physician engineers, you will be making patients feel better while making innovations that will make thousands of people feel better. And that's, I think, what this is all about. So I'd like to just make one more comment and single out one person in the audience who grew up in the civil rights era in Georgia, went to Morehouse College, made his way to Rensselaer Institute in New York for a master's degree, MIT for his PhD, Miami to get an MD, to Atlanta to do a medical residency at Emory, and San Diego to do a postdoctoral fellowship. It was a long journey, and ended up at NIH, where he was became the director of the new Institute of Biomedical Imaging and Bioengineering, and that's Roderick Pettigrew. Rod, you've done so many wonderful things in your life. I mean, looking at this objectively, the EnMed program might be the most historically important contribution you've made, and thank you for that. So my words to the graduating class of 2023 Texas A&M Houston Methodist Hospital is thank you and congratulations.
Thank you, Peter, so much for those marvelous, marvelous comments and stories. I want to just close by thanking our insightful and generous panelists for sharing their insights. I also want to add my infinite thanks to those that Peter's already raised for Roderick Pettigrew for his courage and inspiration in launching the EnMed program. I want to offer congratulations to the first class of EnMed physicianeers. Together, you will pave a path to a brighter future for all of us. Thank you, everyone, for being here on this spectacular occasion.
Hello? Oh,
Yes.
Okay. Please join me in a round of applause for this exceptional, very rare panel, this collection of wisdom and commitment to improving the lives and well-being of everyone everywhere, which is what medicine is all about. We've heard it from them. That's the North Star. Health for everybody, everywhere. Doesn't get any bigger than that. So let's thank the panel, please.
Yes, indeed.
When you put on an event like this, and we're only halfway through, not quite half, we have a small thing tomorrow called a commencement. You don't do that without a large team of dedicated people. We're a small school. So in a small school, you don't have a big team. You have a small team of hard workers, of big workers. And that team is here, and I want to recognize them. Will the members of the graduation committee please stand for our school? And I would like them to be joined by our faculty and our staff. We don't get the students educated without faculty. So all of the faculty also stand. Members of the faculty and our staff. There's faculty back there. I don't know if you saw them all, but they're also dedicated. It's been a couple of hours. Peter's still with us. Thank you, Peter. Peter, by the way, had his own conference simultaneous with this one. He's a director of the Malaria Institute at Johns Hopkins, and they had a conference today on malaria. As you know, they're an hour ahead of us. So they finished around 5:15 or so, and that's when he joined us. So thank you, Peter, for taking the time to join us after your own conference. This event is clearly momentous. It's so substantial, because we're trying to infuse into the healthcare ecosystem a new kind of intellect. We heard about it from the panelists. Phil Sharp talked about the head and the hand. I think that's a great way to describe it. We also heard Peter just now talk about learning and using what you're learning. The head learning, the hand doing. We heard from Marty, who talked about people. You gotta focus on people. That's what physicians do. Engineers solve problems for the benefit of society. As physicians, you're so equipped to solve problems for the benefit of humanity. We heard about humanity from Carolyn. She talked about, and so did Phil, talked about the value of bringing diversity into the problem-solving space, bringing more people into the problem-solving space, and making use of the natural resources that reside in the heads of all of us, and bringing all of that to bear on the challenges that you're facing, with this goal of delivering health for everyone, everywhere. We had a comment that I don't want to go that's not underscored from Carl Wieman. And Carl is right, so he has his own health challenges now. He really wanted to be here. But he talked about it, of learning these skills and learn them in an integrated fashion, and not just one where you pat you on the other. And that's what excites him about this program, and that's what you guys have been trained to do. And we've heard from Marty. I mean, the main thing that you do is you develop an approach. You're not going to get it all done right now. You know, nobody does. You learn the approach. And you use that and you stick with it. So I didn't really intend to kind of get on my soapbox up here. I just really came to thank everybody. But this is what is in me, and it's just coming out. You realize that. So once again, I want to thank all of the participants, the students, those who will graduate tomorrow, the students, those who will follow them, who will graduate in subsequent years, and I see several of you over there. So glad that you came too. From the audience, including those who participated actively in talking to the students about their posters and their innovations. The members who asked questions. That was a wonderful probing question that you asked earlier. And to the staff, once again, and the people who really put this all together and brought this concept into fruition. We have this recorded. This is for all time. It is for our history, for those who will follow you, for those who will follow me, and for those who realize the fundamental value in the approach that we have taken to try and deliver to the world this improvement in the human condition. For those people also, we have this now to provide to them as a way that sort of lights a path to getting us to where we really want to be, this concept of healthcare for everyone, everywhere. Thank you. We will adjourn this event. We can pull back the curtains now and let some of the classic Houston sunshine in. And for those of you who are graduating, we'll see you tomorrow. For those of you who are not graduating, we hope to see you tomorrow also. And Amy, So where's Amy? I can't see. Is Amy still here? All right, so Amy is alias Mama Bear. So Mama Bear is left, but I just wanted to give her a shout out. She's really helped us, Amy and Margie. I do want to say one final thing, and I apologize for going on, but I had this in my mind. When I was at the NIH, NIH stands for National Institutes of Health, and there was somebody there who used to say that NIH really stood for National Institute of Hope, National Institutes of Hope. And that speaks to this issue of humanity and bringing health to everyone, everywhere, for as long as we live. That's really what we're all about. And the person who coined that phrase, the National Institutes of Hope, will be our commencement speaker tomorrow. He's here today. I want to acknowledge his presence with his better half, Diane Baker. Dr. Francis Collins is to the left. All my friends on the front row, thank you for coming. Everybody else, go have a good evening.